Okay, this is section 10.5. It's called Angle Relationships in Circles. I can always think of a better name for these things than they give them, but anyway. What's going to happen today is we're going to draw every time we do a problem, or it's going to be a circle drawn for you anyway. And then that circle is going to, if you want to think about it, it's going to interact with two kinds of segments, secants and tangents. Do you remember what they look like? Do you want me to remind you what a secant and a tangent is first?
Yes.
Okay. And then I'm going to erase this, so I just need to get this idea in your head. With respect to a circle, a secant is a line. So is a tangent. They are lines. They've got arrowheads on both ends. They go on forever. But a secant hits the circle twice on its way through, so that you end up with a chord as part of the secant inside the triangle or circle. A tangent just snugs up against the edge of the circle, so there's only one point of tangency, but it's still a line. And the point of tangency is one of the points on the circle. Remember those two things? So this is a secant, and this is a tangent. And the way things are going to shape up today is we're always going to have a circle and two lines. And those two lines might both be secants, they might both be tangents, or there might be one of each. Okay? And I want to tell you right up front, right now, the most important thing that will help you make the decision on how to solve these is, where do the lines cross? Do they cross inside the circle, on the circle, or outside the circle? Really only three concepts here, and they're all related to each other. But it's where the cross points are. And the reason why I've got to draw several examples up here is because we can have two secants cross inside the circle. We can have a secant and a tangent cross on the circle. We can have two tangents. Well, you'll see. Well, let me just start going on. You'll see. Okay, so here's the first one. If I've just got a plain old circle here and I have two secants and they cross inside the circle. So those are my two secants. They both hit the circle twice. It's not anywhere near the center, so get over that. It's not going to be near the center. I mean, it's not going to be the center. It doesn't have to be. And what we've got here is, I'm going to put some color on this. When I have these two secants cross, if I want to focus my attention on this angle right here, we call that angle X, it's X degrees that I'm going to talk about. Then that angle is related, because you remember vertical angles are equal. If this is X degrees, so is this.
Yeah.
Yeah? Okay. So these two that I'm talking about, X and its vertical angle, are not inscribed, but they belong to these two arcs. Because as you open this one out, it hits this arc, and as you come out the same size, it has the same size angle, you come out this way, it hits this arc. Okay. Now, had I put X here and here, we would have been talking about these two arcs. Do you see it? See how they're related? Okay. The relationship is this. I'm going to put an A up here and a B here, and everything's measured in degrees today. And this is if it crosses inside. That's the most important thing to note at the very beginning. If the cross point is on the inside, and then you look at the angle that they want you to have involved in this, they may tell you what the angle is, or they may ask you to find it. But whatever that angle is, go out along the sides and see that arc, come back the other way on this vertical angle side, come back this way. Find those two arcs, and this is the relationship. A plus B divided by 2 is X. So the two intercepted arcs, the average of them, is the size of the interior angle that they belong to as you flow through here. You follow that? Everybody okay with that?
Yeah.
Okay. I'm going to do several examples for you in a minute. I'm going to do all of this with just variables. And then I will, hopefully you'll have them on your paper or can see them in your book, because I'm going to have to erase this board to stay on the video there. Can you see all of that? Yep. Okay. And then I will cause you to remember these so that we can make a decision. But I'm going to have to erase these. So if you want to take some notes, it might be a good idea. So think about this with me for just a minute. Let's pretend that these are two sticks. They make secant lines. They're inside the circle right now. Let's pretend that I pick this thing up right where they cross. Everything stays rigid. I pick that up and I start to bring it towards B. So I'm going to bring it down this way like this. What will happen to A? Bigger or smaller? if I take this point right here and leave these sticks rigid, they're not going to move. I'm just going to take this point and drag it this way towards the edge of the circle. A will get bigger. Who keeps saying smaller? It's okay. It's okay. I want to know why you're thinking smaller.
Because since you're pulling it back, you're pushing those.
Oh, I see. I see the mistake. Okay. Yeah. No, wait a minute. These are rigid. How they're crossing right now, it's not like a rubber band. These are sticks, and I'm going to pull. I'm not going to move. I'm just going to pull that thing the way they're crossed. I'm not going to let them expand or contract. I'm going to pull them right down like this. I'm just going to take this whole thing and move it closer to the edge of the circle. Can you see now that if these are not stuck, they're not attached. If I pull those down too, can you see that A is going to get bigger?
Yes.
You understand what I'm saying now?
Yeah.
Okay, all right. And what will happen to B? It will get smaller. And if I pull it all the way until this corner hits the edge, then B will go to 0 and A will get bigger, right? So it will look like this. Still working with two secants. If I have those two secants, not exactly those, but any two secants, and they cross on the circle like that, then there is only X and only A, because B has gone to 0. But think about this. If I did that and I said, okay, B has gone to 0, then I could say this. I could say A plus 0, because that's what B's gone to. A plus 0 divided by 2 equals X, because B's gone to nothing. So it's the same thing here. But whenever you add 0 to anything, nothing happens. So what I really have is A over 2, which is exactly what we learned yesterday. Because when you pull that corner to the right on the circle, you have an inscribed angle X, and it is half the arc that it intercepts. Okay? Now, we're going to stick with two secants. What would happen if I took this corner? And again, I'm not going to let the sticks, but they're rigid. If I continue to pull this way, what would happen to A? It'd get bigger yet. And we would open up a B. So I've got an A and a B again. And I got an X here. X has migrated from the inside all the way out to here like this. And again, it has to do with where the cross point is. Is it inside, on it, or outside? This one happens to be inside. And by pulling it clear out of that like that, I've created this B again. But notice what we did. We went A plus B, A plus 0. Guess what we're going to do now? A minus B. B has been turned inside out, if you will. Because it's still inside that angle, but it's not coming out this way that's created from that X. It's all about this X right here. And so we went from B equals B, which was positive, to 0. It's bound to be negative here if we keep pulling it out, which is true. That's a fact right there. So it depends on where the cross point is. If the cross point's inside, you add the two related arcs and divide by 2. If it's on it, you just divide by 2, because we learned that yesterday. If it's outside it, you subtract the two arcs, big minus little, divide by 2. They're all very similar to one another. Now that's what happens if you have two secants. What happens if you have a secant and a tangent to cross inside the circle? Can you get a secant and a tangent to cross on the circle? Okay, so with this one's eliminated because it's impossible. So we'll move to this using secant and tangent and try to get it to cross on and try to get it to cross outside. So here's the next thing I got to draw. So I've got a secant here and a tangent here. And where they cross, I'm going to call that X. I'm going to call this one X. I could just as easily have called this one X to make my point. Doesn't matter which side it's on, but this is the cross point and it's on the circle. The arc, where I put the place on where I put the X, the arc associated with that, you follow, that's the vertex, you follow it on out, and whatever piece of circle is inside that angle is the intercepted arc. Even if it's a secant and a tangent, and it looks kind of weird. But this is A. Now, just like this was A over here, we're crossing on the circle, there will be only one arc and one angle, and it'll be the arc that's inside that strange looking angle there, and it will still be A divided by 2 equals X. So it doesn't matter if it's a secant or tangent or two secants, it's still the big arc that's intercepted divided by 2 gives you X. So these are both inscribed angles like we learned yesterday. Now, can you get a secant and a tangent to cross outside the circle? Think about that.
Yes.
Think we can? I'm getting really crammed tight here. So I've got a secant and I've got a tangent, and they cross outside the circle. And I've got two arcs again. Inside that angle it opens up, but this is X. then this is A and this is B. We call the big one A and the closer one B. And because the cross point is outside the circle, it's still A minus B divided by 2 equals X. Because it's outside, we subtract. Okay, you with me so far? Okay, I might be able to fit one more on there over there. Okay, so here's what we've got. Two secants can cross in, on, or outside. A secant and a tangent can only cross on or outside. The only other option we've got to consider is two tangents. Can you get two tangents to cross? Can you get two tangents to cross inside?
No.
On it?
No.
Not unless they're exactly the same tangent, which would be dumb. Can you get a secant, or can you get two tangents to cross outside?
Yes.
Yes. This one's really, really important. So I'm going to erase all of these others. They're all in sequence and everything's going to happen, but I'm going to erase these because there's a little bit more to this one that I got to write. Okay, so I'm going to erase all of this. And we're now dealing with the last kind of thing, which is two tangents. And the only thing they can do is cross outside. I might bring up one of these things again. We'll see. One of these things that I've erased just to show you the difference. But if I have a circle and I'm talking about two tangents that hit it, maybe something like that one and that one. Cross on the outside, that's not a very good continuation there. Cross on the outside, there are still two arcs. There's A right there, and there's B down here, and there's X here. Here's what makes this one different from all the others. The entire circle makes up A and B on this one. So it is still true, and I'm going to go ahead and write it right here. It's still true that A minus B divided by 2 is equal to X. When the cross point's on the outside, that's what happens. But here's the thing. I don't really have to know what A and B are to find X. As a matter of fact, there's three things here. I really only need to know one, because in this instance, A and B make up the whole circle. Let me show you this. I told you I would do some examples for you. I'm going to do one right now of this one. If I've got a circle like this and a tangent, like I just said, coming in like this and like this, and I tell you that this angle right here is, let's say, 38 degrees, find A and B. And you go, I can't, because what would it be is A minus B divided by 2 is 38. Well, I can't solve that because I've got an A and a B in it. However, I could say, I could rename B as 360 minus A. Because we've got the entire circle when you have two tangents hit it. Does that make sense? Or not? I've used up A degrees going from here to here, A degrees from there to there. That's 8 degrees. What's left for this one? Well, 360 minus what I used for A. Now, that's not true if you have a secant and a tangent. Let me just show you. I told you I'd draw another example. We got a secant and a tangent crossing outside. This is A, this is B because this is X. This piece right here is unknown. So you can't do that with this, but you can with this. And so if I told you that was 38 and that's all I told you, you could rename B as 360 minus A and write it like this. A minus all of 360 minus A. You have to put the whole thing in parentheses because that's what B is. 360 minus A over 2 equals 38. Now you have an equation written only in A by renaming B in terms of A. That can only happen with these. And when I do that, now this is the first time you've seen one of these solved. Now you got all these proportions, they're all over 2 and stuff. But that's over 1, and we know how to solve proportions. It's going to be A minus 360 minus A, which I'll deal with in just a minute, equals, because that's times 1, equals 76. 2 times 38. Y'all see it? Now we do the distribution. I got to distribute that negative. A minus 360 plus A equals 76. A plus A is 2A minus 360 equals 76. 2A equals whatever 76 plus 360 is, which is 436. Divide that by 2, and you have A, which will be 218. So that big old monster arc right there is 218 degrees. To find this one, all you got to do is subtract that from 360. to find the B one. So this is a special case because the two arcs formed by the tangents make up the entire circle. So what I'm trying to tell you is, in this situation right here, you only need to be told one of the three things, just one. And you can find all the others. This is a special case. But still, it's all about where the points cross. Where the line, the segments that you're dealing with, the lines that you're dealing with, wherever they cross will determine whether you're just going to cut it in half, whether you're going to add the two arcs and divide by 2, or whether you're going to subtract the two arcs and divide by 2. So, take a look with me, please, at, now let's take a look at example 1, because the author is trying to point out this weird situation with a tangent and a secant crossing on the circle. So take a look at example 1 with me right there. You see that they're trying to tell you that arc AB is 130?
Yep.
Does it make sense to you that the angle 1 they're looking at is actually a weird looking inscribed angle? Because the cross point is on the circle. And the piece of arc that is inside angle 1 is at 130. And that makes angle 1 half of it, 65 degrees. So it's a strange looking inscribed angle that has the same property. Now look at the next one. You see, now they're telling you the angle KL coming down on the other side on M, that's 125. Since J, the entire great big gigantic red one, is inside angle KL and drop down there, that arc is going to be twice 125 or 250. So it's just a strange version of an inscribed angle. With the cross points on it, you're dealing with inscribed angles. 2-to-1 ratio. Okay, now go over to example 2 on page 563. Where's the cross point? Inside. Since it's inside, I will take A, which is 130, add it to 156, which is B, add those together, divide it by 2, and I now have angle X, which is 143. Catch it?
Yes.
Any problem?
No.
Okay, moving on. Look at the next one. Where's the cross point? Outside. So we will subtract. We take the two arcs that are inside the angle. 178 is the big guy. So we take 178 and we subtract 76. Hit enter and divide it by 2. And that angle X is 51 degrees. You see it? Because the cross point was outside. That will tell you whether to add, subtract, or just cut it in half. Any questions?
No.
Moving on. Go. Look at example 3. This one's a little rougher. Example 3's got some extra stuff in it that I haven't shown you yet today, but you've seen it in this chapter. So they're telling us in example 3A that angle ACB is 135. Doesn't that mean that arc AB is 135 because it's a central angle?
Yeah.
So if arc AB is 135, then we take 360 and subtract 135, and we get 225, and that's arc. That's the big arc AB. I mean, they don't got a third letter for me there, but it's the major arc that goes from A to B, yeah?
Yep.
So now we've been able to figure those out, and they never told us a single thing about the arcs, but we're able to remember the central angle to do that. So I'm going to take the 225, which is the big arc AB, and subtract the little arc, which we know to be 135, and divide it by 2, and we find that X in that case is 45. You got to remember, central angles determine the size of the arc, and that's how this one starts with the Z. Are we okay?
Yep.
Moving on. Ooh, boy, got to find angle X in there. And the angle X is a cross point on the circle, right?
Yes.
Here's one of those situations where I told you, you only have to know one angle to figure out the size of arc EF and arc big arc, well, EJF. You can find both of those big arcs, EF, which is minor, and EJF, which is the remaining major, by knowing what that 30 degrees is. That's all you got to know. I'll find the size of those, and then I'll try to figure out what angle X is. So hang in there with me. Since I have two tangents, I've got this special situation, and I'm going to deal with this part first. The fact that I've got a 30-degree angle crossing outside with two tangents, like this. So I'm going to ignore the rest of the problem because the only thing I'm allowed to find, or I can find out right now, is, oh crap. How about that? It's supposed to be a tangent. Just go with me. It's freehanding stuff. Okay, so this is X. I want to find this and this. And since these are both tangents, I can. For example, now I'm going to do it slightly different so that you see there's another option. I'm going to call this B, but I'm going to call this 360 minus B. That'd be okay? The other way, when I did it before, I called this 360 minus A backwards. I'm gonna call that one B, and this one 360 minus. And remember, the relationship is when the cross point's on the outside, you take the big one, which is 360 minus B, and you subtract the little one, which is another B, and you divide it by 2 to get the angle. You follow all that?
Yep.
It's kind of tricky sometimes. If I cross multiply and combine at the same time, I get 360 minus 2B times the 1 that's over here equals 60. You okay with that algebra? I cleaned that up at the same time I cross multiplied. You see it? This turned out to be 60, and this was just whatever this is times 1, but those added up to 2B as I wrote it down. Negative 2B. You with me?
Yep.
Okay, so I'm going to do a little trick here. I'm going to take 360 minus 60 and toss the 2B over here so that I don't have to deal with a negative. So I put him over here, and at the same time, we do the 60 over here. That's 300 equals 2B, and so 150 is B. So this angle, or this arc right here is 150 degrees, and X, if you'll take a look at it, X that they have up here is inscribed on that. So from yesterday, we know this must be 75. That's a very, very complex problem. We used a lot of stuff that we did today, a lot of algebra here, find out that, and then you got to remember that this X that we're actually looking for is actually inscribed on that arc that we just found. So it's half the size. We good?
Yeah.
X is 75. Do you want me to talk you through it again? Anybody? Some of you are still looking at me like deer caught in the headlights. Everybody good? You understand what happened with all this stuff?
Mhm.
We used the tangents to find that arc because that X we were looking for was inscribed on it. We needed that size arc. Okay, take a look at example 4. We'll work through this and I think we'll be done. All about where the cross point is. It tells you how to write the equation, folks. All right, example 4 says, the northern lights are bright flashes of colored light between 50 and 200 miles above the Earth. A flash occurs 150 miles above Earth at point C. So it's in the range. It's 150 miles above the Earth at point C that you see there. And it says, what is the measure of BD, arc BD? Because that's the portion of the Earth from which this flash can be seen. If you are anywhere on arc BD, you'll be able to see, which is what flashes. If you're beyond BD, if you go down the side of that sphere, you won't be able to see it because the Earth gets in the way. You know what I'm saying? So we would like to know how many degrees that arc is, arc BD, so we can figure out possibly where on the Earth, if we come down that far, what people could possibly see these northern lights. Now, if they occur way, way, way high in the atmosphere, then of course that drops down further, and even sometimes we can see them here, 45 degrees up. You see what I'm saying?
Mhm.
Anyway, so I'm looking for that arc. When we know that C is 150 feet above the surface. 150 miles, excuse me. Okay, it says, and gives in parentheses, says Earth's radius is approximately 4,000 miles. So without the globe of the Earth all taking up all that space and confusing things, I'm going to draw this as like this. We've got this sitting up here, coming down like that, which is a tangent. This is coming down right here, which is a tangent. And this is way, 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 way out of scale, but that's okay. This distance here is 150 miles. And this distance here is 4,000 miles. So you can see how out of scale it is. And we're looking for, I guess I'm going to have to erase that word miles, but that's 4,000 miles. And this is going to come out to that tangent point. This is going to come out to that one. The way they got it drawn.
4,150 because you're above there.
Yeah, so this entire distance, well, no, it's 4,000 from here
Oh.
to here, and then another 150. So you're right, this entire thing is 4,150, which is going to be really important because if we draw lines to those tangent points, do you remember from a previous section that these are right angles?
Yep.
Okay. And that gives us right triangles to work with, whose hypotenuse we know. That's what you were just saying, 4,150. But how's that going to help? I mean, don't we want the size? We want the size of this arc, right? Which means to find that, since the way it's drawn anyway, we don't have any, we got a cross point of two tangents out here, but I'm starting things from here. If I could find that red arc if I knew this angle. Is that right? And that angle is two of these little guys. See what I'm doing? I maybe you don't. I don't know. I'm going to get into one of these right triangles and see if I can figure out what that angle is. So I'm going to draw one of those right triangles outside the thing so we can see what we're looking at. Go down like this. This is the right angle. This is 4,150. I would really like to know this. Is there anything else that we know? Because I don't have enough information to do any trig on that.
Oh, we know the side lane.
Yeah, which one? The one kind of on the bottom leaning that? Yeah,
Yeah.
we know what this is because it's a radius just like all the radiuses in this circle, right? So we know that this is 4,000 right here. And if we have that, we can find the size of this angle. This is going to take some trig. With respect to this angle, what trig function relates this side and this side? Cosine, because with respect to this angle, this is adjacent to it, and this is the hypotenuse. Yeah?
Yeah.
So the cosine of theta is going to be 4,000, or the adjacent, divided by the hypotenuse, 4,150. And to find theta, we have to inverse cosine that. You remember that from your learning so far of trigonometry from last chapter? So it's 4,000, 4,150, and we have to inverse cosine that strange fraction. So that's a tricky problem. Let's see. Mode and then degree mode. Okay. So inverse cosine of 4,000 divided by 4,150. And I get an angle of 15.45 degrees. Is that what you're getting?
Yep.
So if this is 15.45 and this is 15.45, which it is, then this arc's degree measure is 30.9 degrees. Okay. So if you're at the North Pole and you come down 15.45 this way or 15.545 degrees this way on that circle, you'll still be able to see it. Otherwise you won't. You okay, everybody? That was pretty wild. And that required an awful lot of math for you to remember. First of all radiuses are the same length. Secondly, you're going to have to remember your trigonometry and how to find an angle, which requires an inverse function. You got to figure out the right function first, and you got to inverse it on that fraction to find the angle size. Then you got to come back here and double it. A lot of math there. Pretty powerful stuff, though. All right, third page. There we are. So the assignment is, everybody ready to write? 3 through 17 odd, 18 to 23, 25, 34, and 39. That's 17 problems today, so it shouldn't kill you. I think you'll be all right. Remember, it's all about the cross point. Ask yourself where the two straight thingies are crossing. If they're outside, you subtract the two arcs. If they're inside, you add the two arcs. If it's on it, you just divide the big arc in half.